or electrolysis. You need to know that these are negative E's, and so they are non-spontaneous. Therefore, we need a power source. So you need a power source to get these to work. So there are two rules you need to know in an aqueous solution when we do these. That group 1 or 2 will not be reduced in an aqueous solution because water is more easily to be reduced. So group 1, 2 will not be reduced in an aqueous solution because it would rather reduce water instead. And then polyatomic ions will not be oxidized because it would rather oxidize water rather than the polyatomic. So if we have polyatomic ion or a group 1, group 2 metal, and it's in an aqueous solution, then we're going to reduce or oxidize water. And then we're going to talk about electrical charges on these things and bring in a little bit of physics in it. So, any questions before we get started? So the very first thing we're going to do is we are going to do some hydrolysis of water. So if we were to take water, we're going to oxidize. We have oxidized side of water, and then we are going to reduce water. So when we oxidize water, what you can remember is when water is oxidized, we produce oxygen. When water is oxidized, we produce oxygen. We said the oxidized is what electrode? It is the anode. When water is reduced, instead of producing oxygen, we're going to produce hydrogen. And in these, we still have the cathode is where we get reduced. So in this situation, we got to go back and we have to balance it. So to balance it, we need to get 4 H's over here, which means what type of solution is that area going to be if we have H plus over there? Acidic. So it is an acidic solution. So if you can remember, oxidized, anode, acidic, they are all vowels. And we have 4 electrons. If we go to the other one, now we need to balance this out with our oxygens by adding hydroxides. And balance this out. If you think of this as HOH, then I need a 2 here. It gives me a 2 there. So then I need 2 electrons on this side. And we have OH negatives in this reaction, so that means when water is reduced, it is a basic solution at the cathode. So you've got to remember oxygen or water is oxidized, is acidic solution. And then when we reduce water, it is a basic solution. Okay, any questions on that? We're going to use that continuously today. Okay, so let's sketch this. So what we're going to do is we have our cell, our electrolytic cell. It is one big thing. We have in our solution, we have in its water. And then we have our electrodes. We have our positive and our negative. Big difference here is when we hook these up, we have to have a power source. So this is our power source. We're hooking the positive up to the positive, the negative to the negative, and we're still running electrons. Except for this time, we're going to use EPA van. So voltaic, anode is negative. Electrolytic, positive is your anode. So that's the only thing that's different here is what is positive and what is negative. So in this one, our anode is over here, which means that's where we're getting oxidized. And over here is our cathode, where we are getting reduced. We still have electrons running from anode to cathode. Huh? Voltaic, anode negative. Okay, so when it is being oxidized, when water is being oxidized, what happens? We have water going to oxygen plus our 4 H pluses and 4 electrons. So you have got to be able to tell me what is happening, what is going on at each electrode. So over here, we're going to start seeing bubbles. We're going to start seeing bubbles bubbling up and bubbles coming out. And what are those bubbles? That's going to be oxygen gas coming out. And then what we're going to get is right up here next to that positive, we're going to start building. We're going to have our H pluses hanging out here as we're getting our oxygen coming out. Now on the cathode side, we have our H2O plus, or not plus, yeah, plus our 2, was it 2 electrons? We get H plus our OH minus and to balance this out we need a 2OH and we need a 2 here and our 2 electrons. So what's coming out over here? We're going to start seeing things bubbling out over here. And the gas that we're getting out from the cathode side is going to be hydrogen gas. And then we're going to have OH negatives hanging out by the cathode. Okay, so what we are going to see here is we have these electrodes. So what is the electrodes made out of? So the electrodes are not part of the redox this time. So the electrodes are just going to be some type of surface where we can just get things to plate. So if you had something silver and you wanted to plate it, gold, we would put that in there and use that to be a place to deposit whatever we're trying to get. Okay? So any questions over that? You must be able to draw this for me. Okay. So let's draw 4 different situations next. I'm going to draw it once, and then I'm not going to draw it again. So if you go over, if you see that next slide, just on that slide, I would write that in aqueous solutions. So in aqueous solutions, that group 1, group 2 metals and polyatomics are not going to be preferred over the water. That water is preferred over those 2 things. So you have this 4 square. Do you see it on the next page?
Molten counts as aqueous?
Nope. We're going to talk about that. So you have this 4 square here on the next page. So that's just room for you to draw. So one of the things we're going to do is we're going to draw A, which is molten sodium chloride. So here I have my cell again. I have my electrodes. I have my power source with my negatives here, positives there. So that means we are, this is going to be our negative, and this is our positive. And then what we have in here, this is molten sodium chloride in here. So we have sodium and chloride ions. There's no water in there. So what happens is the following. Metals tend to reduce. And since there is no water in this, then that means that we're going to have to go and reduce on the sodium side, where we have, which is our cathode. So that means sodium has to get reduced. So we have Na plus going to Na with our 1 electron. So when we start this and we start this reaction, we're going to start plating sodium metal on this electrode. Okay? This is how they get sodium when we want to use it for experiments or show you guys how cool it is. It doesn't naturally occur, so they have to do electrolysis to get it. Now chlorine, what's going to happen on the chlorine side, which is going to be our anode, we're going to have our chlorine minuses, and it's going to produce chlorine gas and 2 electrons. So now over here, we're going to have this bubbling up, and this bubbling is going to be chlorine gas. So if we take molten sodium chloride, we can get sodium and solid sodium and then some chlorine gas coming out. And then remember that the cathode is reduced and the anode is oxidized. Any questions on that? Yes?
So sodium plating to no, never mind. Sorry.
Okay, yes.
the gas comes out
Mhm.
one side.
Mhm. Yes. Okay, so now let's do, B says to do aqueous sodium chloride. So if we have aqueous sodium chloride, then what is available for us to undergo oxidation and reduction? We have water. What else do we have? We have sodium ions. And we have chlorine ions. So I'm just going to draw arrows here showing we're going to split this up. So we're going to have oxidized. What is oxidized? Which is our anode. And then we have what is going to be reduced, which will be our cathode. Okay, so if we're talking about reduction, what is available to be reduced? Can water be reduced? Yes, water can be reduced. Can Na be reduced? Yes, so Na can be reduced. And then, so the next thing is what's going to happen? Which one's going to be reduced? Is it going to be the water, or are we going to go to the sodium? Water. Why are we going to go to the water? Because Na is group 1, okay? Na is scary to these electrons. We're not going to go towards Na. So we're going to reduce water, and when water is reduced, we get hydrogen and our basic solution. I can write that better. So we get H2 and our hydroxide.
You have to balance it.
Yeah, balance it. I didn't balance it. And our electrons. Okay. What about what's on the oxidized part? So what we're going to get is sorry, let me go back here. Gas. We're going to get H2 gas being produced here. Then on the other side, what is available to be oxidized is, again, water and chlorine. Huh? Chlorine's going to be oxidized, okay? Chlorine doesn't fall into that polyatomic or that group 1, group 2 section. So let's go ahead and oxidize chlorine. So we get 2 chlorines. That's not 2. Chlorine gas and 2 electrons. So what do we produce here is we're producing at the anode site, we're producing chlorine gas. So we're going to produce chlorine gas and hydrogen gas in this reaction.
So, unless it's in group 1 and 2, it will be oxidized.
Or polyatomic. Okay. So next, let's do, what's it say? Aqueous iron 3 sulfate. So now we have water, we have iron 3, and we have a sulfate. So we're going to do anox over here. And over here, we'll do the red cat. So what will be reduced? We know metals tend to reduce. So we have water or iron 3. So which one are we going to reduce? Iron, because it's not group 1 or 2. So we're going to reduce iron. And what we're going to get on our electrode is we are going to make some iron solid. So now on our anode end, what can we oxidize? We can either oxidize water or sulfate. So which one is it going to do? Water. And this time, water is being oxidized, so we're going to produce oxygen. So we're going to have oxygen bubbling out, and then on the electrode we'll produce iron. So you will be given on your test one of these 4 situations.
Are we going to draw it?
You'll just have to tell me what's oxidized, what's reduced, and then what's being produced.
So when you draw one, you still write Na, like on B, you'd still write Na as the cathode bar?
No, the bar would be something like platinum, just something that's not going to be part of the reaction, the electrode. NAs will be floating down inside there, but they're not going to do anything.
So how do you draw? Like this is showing the sketch of the cell.
Oh, so if we were to do that, then we would have, let's see, so you would still have this, you would have your cathode and anode. Over here you would have your H2 coming out, and over here you would have your chlorine gas bubbling out, and then in here you just have sodiums just floating around. Okay. And then over there by the Cl2 electrode you'll have the Cl minuses, and over by the H2 electrode you'll have the OH minuses.
And you just make the left bar negative and right.
Yeah, whichever way you want to do it. However, just make sure you show me which way the electrons are flowing. From oxidized to reduced. All right, and the last situation says a aqueous sodium sulfate solution. So now we have water, we have sodium, and we have sulfate. So if we have our anode, our anox, and over here we have our red cat. So what can possibly be oxidized or reduced? So on the reduced side, we can either have water or sodium. And which one is it going to be? It's going to be H2O, because sodium is group 1, group 2. So that means we're going to make oxygen and H+. No, not H+, OH-, sorry. Whoops. On the reduced is hydrogen. Yeah, sorry. I have it backwards on my notes. H+ and OH- is what we're going to produce on the cathode side. And on the anode side, again, we have the ability to have either water or sulfate, and we're going to choose the water because we have a polyatomic as our other options. So then this time we will produce O2 and H+. Any questions on that? So you must be able to look. You'll be given a situation and tell me what will be produced where. What's being produced on the cathode side or anode side. Any questions on that? Okay, so let's talk about electrolysis and the stoichiometry of it. So what we can do is we can take be given a current and a time, and we can take that and figure out how many moles of copper might be plated, or gold, or whatever. And to do this, what we're going to do is we're going to use Faraday's constant to find these answers. Does anybody remember, you will be given stuff maybe in amps. Does anybody remember what an amp is, also known as? Any physics people? Coulomb per second. Okay, so I would just write, instead of amp, I would put Coulomb per second. So here we go. An unknown metal, M, is electrolyzed. It took 52.8 seconds for a current of 2 amps, so I'm just going to put coulombs per second, to plate 0.079 grams of the metal from a solution containing MnO3. What is the metal? I would practice this problem because I guarantee you'll see it on your test too. So, first of all, we care about M. So what is the charge of M? +3. So M is +3. And if we balance that to go to M, then that means we need 3 electrons. So the next thing I need to do is I need to figure out how many moles of M was produced. So I start with the easiest thing that I know. I know that we had a time of 52.8 seconds. I have to get these seconds to moles somehow. So I can use coulombs per second. So for 2 coulombs is 1 second. Now that we're in coulombs, we can use, what's next? Faraday's constant, 96,500 coulombs for every 1 mole of electrons. How many moles of electrons did we use in this reaction? 3 moles of electrons, and we have 3 moles of electrons for every 1 mole of our unknown M. So how many moles of M took place in this reaction? From this equation up here, this balanced equation? Yes. So how many moles of M? Did you get 3.67 times 10 to the negative 4?
Yes.
3.67 times 10 to the negative 4 moles of M. Okay. It's close enough. Okay, so now how do we find out what the metal is? So we have the mass of the metal, which is 0.0719 grams, and we can divide it by how many moles? 0.000367, and get me the molar mass. What'd you get? 195. I got 196.99. So we can round it to 197. So 197 grams. So look at the periodic table and tell me what metal that is.
Gold.
Gold. Questions?
How do you avoid getting it hot by a little bit? Like, if you round from
Where did you round at? Did you use 96,500 or did you use...
I use your number.
You used my number?
Yeah.
I used and I put in that, and then I got 3.64. And then when you got that, it was about to be around like 198.
So if you use 3.64, it's closer to 197? Is that what you said?
6, 7.
Over it? So if you use 6.7, it's...
And if you use 365, it almost say exactly it's not like hundreds of grams.
Okay, so, I mean, the thing is if you can justify, like, I mean, because your options are platinum and gold, really. So if I looked at your number and it's closer to gold, then I would say gold. If you look at your number and it's closer to platinum, then I would say platinum. That would be your justification looking at that. Okay.
So we would use the 485.
Is that what's on there? I don't think it really matters. But if you, on the AP exam, I would just use whatever they give you.
I was wondering if it's not like it doesn't work. So it's not like us.
Yeah. So, all right, I'm going to avoid this one. It said, or not avoid, I'm going to not do this one, but it says consider a solution, predict the order that it's going to play out. So it would probably play out, I would say, if you look at your chart, whatever's higher up on the chart's going to start plating out first, and then it'll just run down. So if you're looking out at your pink, then copper would plate out first, and then it would just follow in succession all the way down.
So it's just activities.
Yes, it's activity series, yes. Okay. Next, let's do another problem, and we're going to do a couple of these and then we're done. So calculate the mass of copper produced during the passage of 2.50 currents through a solution of copper 2 sulfate for 50 minutes. So the very first thing I would do is, since we are dealing with electrons and stuff, I would go ahead and balance the half reaction that we care about. So if copper is being reduced, then this would be our half reaction. So then start out with the easiest thing you know, coulombs per second or 50 minutes. I would probably start out with 50 minutes. So 50 minutes, and we need to convert that to what? We have coulombs per second, so we probably need to convert that to seconds. So 60 seconds over 1 minute. Now that we're in seconds, we can use our amps, so 2.5 coulombs per 1 second. Where's our next step? Faraday constant, so 96,500 coulombs for every 1 mole of electrons. We need to get moles of electrons to moles of copper. So for every 2 moles of electrons, it was 1 mole of copper. And we need to convert copper to grams. So for every 1 mole of copper, it is 63.55 grams. And what do we get? Like how that just got smaller and smaller as I went across. I started getting like zooming in more and more. 2.47? All right, so the next one is just like what we did a while ago, except for this time we're using liters of oxygen. So if you want to later on work this problem, then the answer to this problem is 0.435 liters of oxygen. So work that problem later, and I'm going to do the last problem on our notes. An aqueous solution of unknown salt of chromium. So we know we are dealing with chromium. Is electrolyzed by a current of 3 coulombs per second for an hour. The process produced 1.94 grams of chromium at the cathode. What is the oxidation state of chromium in the process? So we know that chromium is being reduced. We know chromium, we don't know what its oxidation state is, and we know whatever its state is, that's how many electrons are going to have to be transferred. So if it's a +2, then we have to have 2 electrons being transferred, 2 moles. But we don't know what it is. So our goal is to figure out what X is. So we want to know, first of all, how many moles of chromium did we make? So we had 1.94 grams of chromium. And for every 1 mole of chromium, we have 51.996 grams. So how many moles is that? Point 0.0374 or 3? So 0.0373 moles of chromium. Now I want to know how many moles of electrons were transferred. So I know that we had a time. What time passed was an hour. So how many seconds are in an hour? 3,600 seconds. And our amps were 3.00 coulombs per 1 second. So how can I get these to moles? Use the Faraday constant, 96,500 coulombs for every 1 mole of electrons. So how many moles of electrons passed? And that would be 0.112 moles of electrons. So I want to know how many electrons was that. So if I have 0.112 moles of electrons, and there was a total of 0.0373 moles of chromium, then how many electrons got passed? Answer, answer, answer. Let's go, let's go, let's go. 3 moles of electrons. So our oxidation number on chromium is a 3 plus. Okay, so you're going to be given on your test a situation where you're either going to have to tell me the charge or you're going to have to tell me what metal it was. So I would practice the stoichiometry, and it is in your homework. Your homework is part D tonight. I think it's just one page, isn't it? Okay, so that is your assignment, so you have plenty of time. You got about 15 minutes to work on that.